Professor Mendonça?
Mendonça, yeah.
Mendonça. The title of the talk is Time-refraction, Classical and Quantum Optics.
Thanks. So, good morning, everybody. Oh, sorry. I'm going to talk about a very simple process, which is good because late afternoon we are very tired, and well, I think this can be understood by everybody. I nearly understand it, and this is a simple process which has been ignored for some time, but in recent years has been used more and more in classical and quantum optics. So it is, I think, time to review its properties. So what is time refraction? Let me see. I'm a plasma physicist, but I thought I could not talk about plasmas in this audience. So I chose a subject that brought me in contact with Victor. So that's why I think this was appropriate to choose this subject. By the way, we met some time ago, Victor and I. We are here in Lisbon in 2010. In the middle, there is a metallic guy. He's a lottery ticket seller. So not a famous guy, he's a lottery ticket seller. And this is in the city center in Lisbon. So what I'm going to talk about is a short review of the space-time symmetries and talk about temporal Fresnel laws, temporal beam splitters, time crystals. These things are more or less known. And now I talk about a few, 2 or 3 new results concerning temporal gates in Rydberg atoms, time refraction without time, which is strange but can be understood easily, and then time refraction in QED, meaning QED with electron positrons, not just the optical QED. So let me see how I can present that. Actually, I started this work when I was trying to understand perturbations induced in the plasma by intense and ultra-short laser pulses, where time and space were equally important. So I could understand at that time, or a little bit later, that we in these situations you have space and time processes working together at the same time, and you can see the different processes associated with space and time. Newton spectroscopy is well known. With the prism, you can separate white light into different colors. But if you could take a single portion of the spectrum, or let's say a single color, and use it in a temporal device, then you can regenerate white light. So there is a kind of symmetry, not complete. It's a tricky symmetry, but interesting symmetry between space and time. So in a time-varying medium, we, in a sense, reverse spectroscopy, and in intense short laser pulses physics, you mix the two things at the same time. So let me see. Well, this is the simplest possible picture, because sometimes I don't understand the physics. I simplify, and then I arrive at trivial things like this one. This is primary school refraction, and this is, I hope in a few years it will be secondary school because it's so simple. So in the refraction, you break space symmetry due to the border between two media with the refractive index N1 and N2, and this gives you leads to the famous Snell's law that was nearly stolen by Descartes, I think, but it's Snell who derived it first. It relates the incident and the transmission angle, and this is in this case you have the frequency of the light of light is conserved because you have conserved the time symmetry, but the momentum is not conserved, and this is the reason why this equation, this relation occurs. In time refraction, you can imagine something similar where you have an infinite medium. Forget about boundaries. You just have a temporal boundary. So suddenly, one medium with refracting index n1 changes into a refractive index n2. How this is done, we can discuss later, but this can be done. So you have this kind of similar process where you have a transmission signal, and you also have a reflected signal. Of course, you cannot have reflected signal here as you had here, because here you cannot go back in time. Unfortunately, because for me and Victor, it would be very nice if we could go back in time. But this is forbidden, although we can go back in space. So this is, in a sense, you break the time symmetry here, so the momentum of the photons is conserved, of light is conserved, and due to that, you have a new relation between the frequency of the initial and the final frequency of the medium, related with the change in the refractive index. So this is the classical picture of what I call time refraction. Of course, you can say, well, if the frequency of light changes, there is some energy going in. You have to inject energy. There is hidden energy in the transformation of refractive index. That's the origin of you need an external source to transform refractive index. That's why you have energy available to transform the frequency. Fortunately, this is observed experimentally, so this is not a mathematical speculation. So this is my starting point in this area was that one, and then I did. This was in the 90s. I started working on these problems, and then around in 2000, I thought maybe I could be more sophisticated and use a quantum description. So in 2000, I did some. Well, I used I skipped that because it's late and you have to squeeze a little bit the presentation. So in 2000, I did the same thing using operators, and I derived transmission and reflection coefficients depending on the change in frequency, and then I calculate the emission of photon pairs. And later on, a little bit too late actually, because I didn't cite this paper by Victor, I realized that Victor had done similar things a few years before. Not exactly the same, because the approach and the purpose were different, but there are similarities between these two papers. I think that's why we end up having some contact. Yeah. So what next? Then what we did, we looked into experimental observations. In plasmas, what we did, well, people did in the past, the first observation is, published observation is from Jablonovich in 1974. He called it flash ionization. He focused a CO2 beam in a gas, and he observed the ionization, and he observed a blue shift of radiation. So he observed this tail was longer than that tail, blue shift. And he called it self-blue shift. This is very well explained by the temporal Snell's law, because initially you have nearly vacuum, and then all of a sudden you have a plasma, and the dispersion relation is modified, and you have here an additional quantity, which is the plasma frequency. So these blue shifts, they are observed nowadays in laboratory with big lasers, and for instance, with near petawatt lasers, you can observe here in red. You observe. You have two examples, experimental examples, recent examples, and you have here when you focus in the gas, you have ionization. Suddenly, the red spectrum is transformed into blue spectrum. You see a shift which depends on the energy or intensity of the laser. This is when with 14 millijoule, this is in 200 millijoule, and you have here a shift which is increases with intensity because it increases with the plasma density. And I forget these things because it's somewhat complicated, also interested, but they are for another kind of talk. So these are observations in optics as well. But people try to ignore these things until recently. But now I go to the quantum part of the exercise. It is well known that quantum optics, this is one experiment that is probably at the beginning of quantum optics. It's one of the experiments that motivated really the development of quantum optics, the optical beam splitter, where these guys, Granger, Roger, Alain Aspect, they shown that one photon can interact with each other, and similar things like that. Formation of entangled state, single photon effects, what they call cavity QED. Of course, people from my area using petawatt lasers, they say QED, that's what we do, not what they did, because it's electron-positron QED. But people call it cavity QED, the development that followed these kind of experiments. And then later on, quantum computation. So these kind of experiments are related to a property associated with photon number conservation. But of course, if you change the optical beam splitter by a temporal beam splitter, then you have photon creation. And this is what is a temporal beam splitter. You imagine a medium which can be the air or vacuum, and then you suddenly create a medium with a different refractive index, and after some times you go back to the initial situation. And using that, you can not only you have transmission and reflection coefficients, which are different from the space ones, but you also have production of photon pairs. Why photon pairs? Because we don't have no boundaries, and the photons, there is conservation of momentum, so you need two photons, equally frequency photons, created simultaneously to conserve the momentum. And then you have this creation of photon pairs. Of course, if you had boundary effects, you transform this problem into what is known by dynamical Casimir. But the bottom line is that time refraction, for time refraction to occur, you don't need boundary conditions. You don't need boundary effects. And this is also related with Unruh. Actually, I try to understand. I know that these three things are closely related, but I try to do some. Oh, let's see another before that. You can imagine a sequence of temporal beam splitters, and you end up with something that you could call a temporal cavity, but which is more closer to a dynamical Casimir without boundaries. And you know the work of Victor in this area, in particular his recent review on the work 50 years, 100 years, how many years of 30? 50 years. Not 100, no, not 100 years. But of course, I wonder so this is the connection between the dynamical Casimir and the time refraction. You can imagine in time refraction, you put a boundary just to be closer to dynamical Casimir, but you consider fixed boundaries. So you select photon momentum here, and then you change the refractive index. This, optically speaking, this is equivalent to change the length of the cavity. So these two things are related, and of course it's nearly the same thing. And again, I suspect time refraction, dynamical Casimir and Unruh are intimately related. I did some work using a cavity with two Swedish colleagues. To be frank, I was happy because Unruh in a couple of recent papers, he quoted this work, but I'm not satisfied with this work because the work doesn't really explain that these two things are closely related. Sorry? Yeah, what I did, yeah, I'm cleverer than that, not than you, but than that. And actually, what I did was I studied the motion, of the moving mirror and interacting with the vacuum fluctuations, and studied the radiation coming out of the motion of the. So that's why I know these things are intimately connected, but I don't really explain clearly. Maybe some people like you eventually can do it, but I don't explain really clearly the connection between them. But they are intimately related with the non-conservation of energy in the vacuum. Recently, to my surprise, actually, time-refraction was dormant for this concept for several years. And, well, 6 or 10 years ago, this thing started to move, and there is a lot of work, especially in optical metamaterials, dealing with this kind of effects. I give you this just an example of this guy's recent paper where they rediscover these things, the temporal reflection and these kind of things, the temporal Fresnel laws. They rediscover that. But so these things are now moving very fast and getting some importance. Unfortunately, this is only true for the classical aspects of time refraction. For the quantum aspects, there is still very little experimental work, if any. So these guys, they did that. What I did recently, but I skipped that. I go very fast because I want to finish early. And I did temporal gate in Rydberg, in the gas of Rydberg atoms, because Rydberg atoms are very sensitive to temporal changes, because the transmission through the gas, it depends very much on the frequency. So you can shift using dynamical Stark effect. You can shift the refractive index of the gas, and then introduce a kind of temporal gates which can have for typical using femtosecond pulses, you can use femtosecond gates. But I skip that. What more interesting is this, which is time refraction in superfluid. It sounds very complicated, but it's not. Superfluid light, and it's a case where time becomes space, which is, I mean, I can observe a temporal process in a static situation. I explain it better. When you propagate a photon beam in a nonlinear Kerr medium, for instance, a nonlinear crystal or a gas tube with a nonlinear refractive index, the envelope equation describing the beam satisfies the nonlinear Schrodinger equation. And if you change space with time, you have this appears to be in the perpendicular direction. The evolution of the electromagnetic field can be associated with a kind of, it looks like, I don't say it is the same, it looks like a 2D Bose condensate. And the thing is that then if you propagate a beam and you follow the axis of the beam propagation and you cut successive planes of the beam, you have kind of successive instants of the beam propagation. And if you have a static boundary here, it looks like in the frame of the nonlinear Schrodinger equation, looks like a temporal effect in the perpendicular plane. So what we have here, we have photons propagating here, and being reflected and transmitted through the boundary. And at the same time, in the perpendicular plane, you have these diffraction waves which can be excited eventually by obstacles in the perpendicular plane. And these diffraction waves, they satisfy, because they are described by an Orlin Schrödinger equation, they satisfy Bogoliubov dispersion relation. So they have a Bogoliubov speed, and they have, I can call them bogolons in order to do. They are diffraction waves actually, but they can be called phonons in this 2D pseudo condensate. I call them bogolons. That just to so the photons have the usual space refraction, the good old refraction from the primary school, let's say, and the bogolons, they have time refraction, secondary school in a few years, and they observe frequency shift, partial reflection, and refraction, and amplification as well, because there is no energy conservation, but observe in the perpendicular plane. So you can excite using a boundary, you can excite diffraction waves going in the perpendicular plane. So these things. So if you have a propagation, a perturbation going on in perpendicular plane, at some point suddenly, after this boundary, which is space, it looks like time, you have reflected and transmitted signal with an eventual amplification of the signal. If you have two boundaries, you have the optical, the temporal beam splitter again, and you have this kind of things. This can be done experimentally by changing refractive index in some region. This can be done in a Kerr medium. This can be done by using a beam in propagating perpendicular to the direction of propagation of the primary beam. So you have these two boundaries here. So you have then a situation where time becomes space. Well, you can do that more fancy things using simulations based on the Gross-Pitaevsky or Norlin-Schrödinger equation. And for instance, in this case, if you excite some perturbation which creates a diffraction here, but if this medium in this region has no linearity, is linear, so it has no superfluid properties, so nothing happens here. But as soon as the medium becomes superfluid, then you see a cone propagate in the both directions with the velocity given by the Bogoliubov speed, propagate in both directions because you have conservation of momentum and you have create pairs of, this time pairs of phonons, or you can say pairs of bogolons instead of pairs of photons, but it's the same process. They are bosons actually. And if you go, the interesting thing is that if you then switch off the nonlinearity, these diffraction waves, they don't propagate anymore, but they stay there. They are not attenuated. So here I have a more complicated process. So this is funny to study, to show to the people, but and it is feasible. We are doing actually an experiment in the lab using a tube of rubidium, hot rubidium at 80 degrees, between 80 and 100 degrees, just to have a good nonlinearity. Of course, if you introduce a periodicity in these perturbations, space perturbation, you have a temporal kind of time crystal, but in space. You have let's say a frozen time crystal, and you can extract a temporal Bragg formula defining the situation. You have a strong reflection out of this crystal. Of course, probably I can tell you a couple of things about time crystals. This was defined proposed by Wilczek in 2012. He didn't ask me or Victor if this was a good idea or not. we would have told him that this was wrong. Yeah, his idea was wrong, but because it is Frank Wilczek, well, you have to. The guy is a Nobel Prize, so you should take that seriously. So the idea of tram crystals started to be developed, but it could be called dynamical Casimir or temporal cavity. This is the same thing. But of course, the thing is that in our models of the dynamical Casimir or time cavity, temporal cavity, we are injecting energy. But here he was proposing that a medium would make a transition, a symmetry breaking, going into a lower energy state. And then a few guys then suddenly tried to convince him that this was wrong, and indeed this is wrong. It needs, you can build this kind of crystals, but they need to be open systems where you inject energy from the outside. This is not the spontaneous symmetry breaking that was dreamed by Wilczek. It's a pity he didn't ask you, Victor, because this was really silly. Anyway, but a few years later, we discussed that because in my lab, I have a small experiment on rubidium atoms. We have typically 100 microkelvin in steady state here in a nice box, and this the ultra cold cloud we create, it has 10 to the 10 or 10 to the 9 atoms, and it depends very much on the frequency shift between the frequency of the cooling lasers and the frequency of the atomic transition. These are strongly coupled systems, so the shift is very small. But if you change the shift, you change the shape, and you compress or dilate the volume. So we thought the same way if you change the intensity of the cooling system. So we thought if we change the delta or the intensity, this thing will do something like that. And because this is a kind of dynamical Casimir thing, we can create not photons here, but phonons, because phonons can propagate in this model. So that's why Victor and we did some sketchy model estimating the number of emitted photons and showing that this is plausible. So sooner or later, I hope that in a few years you'll have an observation of dynamical Casimir with creation of phonons from out of the phonon vacuum. Finally, just I'm about to finish QED vacuum particle pack creation, because people used to say, well, this is QED. You are not doing QED. This is quantum optics is not QED. So I said, well, let's do QED. So I was in the COVID confinement at home. I took this very good old Klein model, and I considered the temporal equivalent and studied the creation of photon pairs from out of this sudden. It's the opposite of the Schwinger model, because Schwinger model is an infinite field, a constant field. Here is an instantaneous field, and it creates lots of electron-positron pairs. But of course, any arbitrary electric field can be decomposed into a series of infinitesimal temporal Klein processes. So, well, like this, like here. So if you do that exercise, you derive something, you feel very happy. You can derive an equation of evolution for the number of electron-positrons pairs created in the medium, in the vacuum actually. And then you realize that this was done already in 98 by these guys. It is well-known result, but the good thing here is that we obtain it from a completely different perspective using the time-refraction concept. So in a sense, this is new and not new, but conceptually is very reassuring. So these equations are right now being done in order to understand the possible the possible breakdown of vacuum using multi-petawatt laser pulses, and people think that in a few years you'll have observation of this vacuum breakdown, and this can be described with this kind of kinetic equation, where F minus is the number of electrons created, or positrons created from vacuum. So in conclusion, I told you a little bit about the space-time symmetry. I'll call your attention for literature, in the recent literature on, especially in metamaterials, on time refraction. And I went through all these examples, more or less fancy, more or less useful, more or less speculative. And then I think that this concept will have some importance in the temporal optics that is being done today. But I'll have to say that evidence of classical effects is good. Evidence of quantum effects as creation of boson pairs is still missing. Thank you very much.